In this video I describe manual control of the tight azeotropic pot still. The isothermal deflegmator described in my previous video has the advantage of allowing a higher alcohol proof and avoiding the tails of a distillation run. But arguably its most significant advantage is how it simplifies column control. It accurately and automatically controls column cooling, whereas many moonshine column cooling methods require manual control of a cooling parameter, such as the rate of flow of cooling water through a column head condenser, or moving such a condenser in or out of the top of the column. None of that is required with an isothermal deflegmator, the only thing being to monitor the level of spirit, which may need to be topped up every few days, depending on how effective the reflux condenser is. This leaves only one parameter that needs to be controlled, the power to the boiler, and it needs to be controlled quite precisely. It is controlled in response to measured parameters, the main one being the proof of the product as measured by a Parrott hydrometer, compensated for Parrott temperature. A simple spirit hydrometer covers the alcohol concentration range of 70 to 100%. It's small with a diameter of about 15 millimeters, so easily fits inside a 22 millimeter pipe. They are relatively robust and are widely and cheaply available. The problem is that they're not very precise. They're generally graduated into whole percentage points of alcohol by volume, ABV, and you can judge intermediate positions, but it's difficult to judge more accurately than a quarter to a half a percentage point. That's fine if you're only trying to get over 95%, in which case you don't really need a 1500 millimeter column. A 1 meter column would do. If you're trying to get over 96%, you need to be able to plot the alcohol with a precision of a tenth of a percentage point or better. This requires a specialist precision hydrometer, graduated in tenths of percentage points and covering the range 90 to 100%. They are larger than ordinary hydrometers, requiring a 28 or 35 millimeter Parrott. They're also more expensive and considerably more fragile. That can be a problem because they probably have to be ordered from China, and they are not always packed to withstand the abuse of Western postal services, though in my experience their sellers are happy to replace ones that get broken in transit. The larger size means that the Parrott is larger, which leads to a slower response time as it takes longer for the Parrott to fill. If you're in doubt, start with a simple spirit hydrometer. If you know you want to go for the highest possible proof, get a precision one and a spare. You'll be breaking them. Both precision and standard hydrometers need to be temperature compensated, so the Parrott needs to have a temperature well and a thermometer. This column distills slowly. It will take between half an hour and 2 hours to fill the Parrott, depending on whether a small conventional or a large precision hydrometer is being used. So adjustments to the still will be made infrequently. Secondary parameters that contribute to control are the temperature of the top of the column, the temperature of the bottom of the column or boiler, the current boiler power setting, and the time since the beginning of the distillation run. Ambient temperature and atmospheric pressure are also useful to record, not because you use them to control the column, but because its optimal power setting will vary with these, and noting them will give you an idea of how, helping with future runs. This graph shows product proof, flow rate and column top temperature against boiler power, with a constant wash alcohol concentration. With boiler power under, in this case, around 100 watts, no product is produced, so its proof cannot be used as a control parameter. As you approach the point where product starts to be produced, the column top temperature rises rapidly. Beyond that point, the column top temperature rises less rapidly, the alcohol concentration falls, and the volume per hour of product increases slightly. You can see that the optimum alcohol content occurs just at the point where the product starts to be produced, meaning that below that point we don't have a reliable parameter for what power to set, whereas above it we do. That's why the control protocol is to start by overshooting and adjusting back down, guided primarily by product proof and secondary by column top temperature. As the run progresses, the alcohol content of the vapour coming off the boiler falls. The column requires a constant alcohol vapour flow rate, so we have to increase the power to the boiler to allow for this. These increases will be small and infrequent early in the run, but become faster and more frequent as the run nears its end. For this still, the power range will be somewhere around 100 watts at the beginning, raising to somewhere around 350 watts at the end. You can distill wash straight out of a fermenter, but it is easier if the distillation run is longer because it requires less frequent adjustments to its power setting. As the column will distill about 50 ml of alcohol per hour, if you start with a 50 litre boiler with wash of say 14%, that gives you 7 litres of alcohol, which will take 140 hours or about 6 days to distill. That's perfectly feasible, but it makes your life easier if you do stripping runs from wash to 35 to 40% ABV. When you've got 50 litres of that, distill it. That gives you around 20 litres of alcohol, which will take around 400 hours or 17 days to distill. That makes your life a lot easier because the alcohol content of the vapour changes much more slowly with time when there's a higher ABV in the wash, giving you ample opportunity to find the optimal operating point of the column without the complication of compensating for the changing alcohol vapour concentration as the run progresses. Start by setting up the still, filling it and turning the heater on at full power to raise the temperature of the wash from cold to boiling point, which in my case takes about 2 hours. Use the column bottom or boiler temperature to monitor this. Depending on your wash concentration, when it's boiling the temperature will be a bit over 80 degrees centigrade at the beginning of the run. When it is, change the heater over to precision control and to begin with set it at about 80 watts, which will probably be too low to produce any product. Wait until temperatures have stabilised, which will take 10 to 20 minutes. Then note the column's top temperature and whether there's any product. If the top temperature remains low, then increase the power by 10% and repeat. Continue until you get product produced, which will likely be at around 100 watts. When you have a full hydrometer, note the product proof. It will probably be in the low 90s%. Then reduce the power by 1% and repeat. Continue to do this, recording and plotting the alcohol proof against power. This will give you a good idea of the column's characteristics. The product ABV will get higher and higher until production stops. From that you'll get your optimum power setting. Thereafter you're going to slowly increase the power of the boiler to keep the column at this optimal point while the alcohol content of the wash falls. Once you've got that sorted out, you can turn attention to the column extension temperature. To begin with, I would set this at 70 degrees centigrade. The column separates heads from hearts. Heads comes out of the top of the extension as vapour. Hearts are drawn off as liquid from the draw point. The temperature of the extension determines the ratio of heads to hearts that you get. At 70 degrees, you'll get about 10 parts hearts to 1 part heads. If you reduce this temperature below 70 degrees, you'll get more hearts and less heads, but you'll get more headsy flavours appearing in the hearts. Conversely, the reverse happens if you increase it above 70 degrees centigrade. When I did a blind tasting, the taste difference was noticeable between about 66 and 70 degrees centigrade. Over 70 degrees, I struggled to notice a difference, which is why I settled on this figure. However, your taste may be more sensitive than mine, and calibration of temperature sensors does vary, so you may find by experimentation that the optimal temperature for your column extension is slightly different from 70 degrees centigrade. As the run nears completion, the boiler or column bottom temperatures will approach 98 degrees centigrade. The limiting factor will probably be the ability of the isothermal deflegmator to remove heat. It will bubble increasingly vigorously until spirit droplets start to appear overflowing the condenser. By that point, there will be well under 1% of alcohol left in the boiler. Turn it off and let everything cool down. I hope this will be enough information to get the pot still working with manual control. In the next video, I will turn to automation.